So now we're looking at the superposition principle or theorem. So we're going to let x1, x2, all the way up to xk be a set of solution vectors of a homogeneous system. X prime is equal to ax. Then the linear combination, and we've talked about this several times, especially back in chapter 4, the linear combination C1 x1 plus C2 x2. So each of those solution vectors can have a coefficient, and they're arbitrary coefficients, and they are going to also be solutions. So again, if you remember back to chapter 4, we talked about this, the C1, C2s. So our example, given x prime equals 1, 3, 5, 3, x, we want to show that there's these solutions. Solution 1 is 3, 5 times e to the 6t. And then we're going to show another vector that's also a solution. So first, again, I want to rewrite this by distributing that e to the 6t to both the terms. So on the left hand side, I need x prime, or x1 prime, and that's going to give me 18 e to the 6t and 30 e to the 6t when I take the derivative of each of these entries. So that's the left hand side. And then on the right, we have this coefficient matrix times x. And here's my x. So when I multiply that out, I get 1 times 3 e to the 6t, which is 3 e to the 6t plus 15 e to the 6t. And then the bottom, I get 15 e to the 6t plus 15 e to the 6t. So add these two together, and I get 18 e to the 6t, which matches here. Add these together, I get 30 e to the 6t. So because those match, then I know that that is a solution. And then we have another solution vector, x2. So again, I need to do a rewrite. And I get e to the negative 2t and negative e to the negative 2t when you distribute that. So the left hand side, the x2 prime, gives me negative 2e to the negative 2t and positive 2e to the negative 2t. Again, I have the same coefficient matrix, 1, 3, 5, 3. And then I'm multiplying it by x2. So e to the negative 2t, negative e to the negative 2t. So when I multiply it out, I get e to the negative 2t minus 3 e to the negative 2t. And then 5 e to the negative 2t minus 3 e to the negative 2t. So when you subtract these, I get negative 2 e to the negative 2t, which matches. And down the bottom, 5 minus 3, I get 2 e to the negative 2t. So those two match, so therefore it is a solution. So since they're both solutions, then the linear combination of those is also a solution. So we have these arbitrary coefficients, but all those linear combinations for however many solutions I may have is also a solution. And then we're going to talk about the fundamental set. And again, we talked about this earlier in the semester. So the fundamental set is any set x1, x2, all the way to xk of linearly independent solutions. So all the solution sets are they're linearly independent on I, some interval I. So what's the criteria? It's very similar to what we did back in chapter 4. And we're going to use the Wronskian. So we're going to take the Wronskian of that set. And if it's not equal to 0 for every t on the interval, then it's linearly independent. If it is equal to 0, then we know that there's some dependence in there. So I want to show that x1 and x2 form a fundamental set. E to the negative 2t and negative e to the negative 2t. So this is the same one we were just looking at. So we have x prime is equal to 1353x. So we already showed their solutions. That was the last example. Now we want to know if it's a fundamental set. So now I'm going to use the Wronskian to show that. So we have x1 and x2. So I have 3e to the 6t, 5e to the 6t is x1. x2 is e to the negative 2t, negative e to the negative 2t. And then we just have to do the cross products. So I have 3e to the 6t times e to the negative 2t. And that will give me negative 3e to the 4t. And then subtract in the other direction. So minus 5e to the 4t, which gives me a negative 8e to the 4t, which is not equal to 0 for any value. So therefore it does form a fundamental set. So our solution is C1 5e to the 6t plus C2 1 negative 1 e to the negative 2t is the general solution. Right? So we proved that these are linearly independent vectors, and then the general solution is just writing that as a linear combination.